Today we are going to learn about building multimodal AI models, a hands-on guide. You will learn how to integrate text, vision, and audio into AI models, gaining the skills to create and refine multimodal AI systems.
Welcome to Building Multimodal AI Models, a hands-on guide. In this video, we will explore the fascinating world of multimodal, an advanced field where AI systems understand and interpret data from multiple sources like text, images, and audio. Multimodal integration is crucial for developing AI that can interact with complex environments, similar to how humans perceive the world. Throughout this session, you'll learn about the practical steps involved in creating these models, from data preprocessing to model evaluation. Let's dive in. In this section, we will delve into the individual components of multimodal AI models: text, vision, and audio. Each of these modalities plays a crucial role in how AI systems interpret data. Text modalities allow models to understand and process natural language, which is essential for tasks like sentiment analysis and language translation. Vision modalities enable AI to interpret visual data, powering applications such as image recognition and object detection. Audio, on the other hand, is key for speech recognition and sound classification. One of the biggest challenges in multimodal AI is handling the diverse nature of these data types. Each modality requires specific preprocessing techniques to ensure they are accurately represented in the model. For instance, text data often needs tokenization and embedding, while images might require resizing and normalization. The key to successful multimodal integration is ensuring a balanced representation of each modality in the model, which we'll explore in more detail in the upcoming sections. Preprocessing is a critical step in building multimodal AI models. It involves cleaning and transforming raw data into a format suitable for model training, ensuring that the data is consistent and compatible across different modalities. For text data, preprocessing typically includes steps like tokenization, where text is broken down into individual words or tokens, and word embedding, where words are converted into numerical vectors. This helps the model understand and process natural language effectively. Vision data, which involves images and videos, often requires resizing, normalization, and sometimes data augmentation to enhance model performance. Images need to be standardized in terms of size and pixel values to ensure consistency. Audio data preprocessing includes tasks like noise reduction, feature extraction, and sometimes conversion into spectrograms. These steps help in isolating relevant audio features that the AI model can learn from. The ultimate goal of preprocessing is to create a dataset where each modality is compatible with the others, allowing for seamless integration and effective model training. Aligning different modalities in a multimodal AI model is a challenging yet essential task. This process involves synchronizing data from diverse sources to ensure they work together seamlessly. One common challenge is temporal alignment, which is crucial for time-dependent data like audio and video. Techniques such as dynamic time warping can be employed to synchronize audio with corresponding video frames. Spatial alignment is important for vision data, ensuring that objects in images or videos are consistently represented across different frames or perspectives. For text data, semantic alignment is key, ensuring that the meaning of the text is preserved and aligned with the visual and audio content. This might involve using techniques like cross-modal attention mechanisms. Successfully aligning different modalities ensures that the model can interpret and respond to complex environments in a cohesive manner, a crucial step for building effective multimodal AI models. Choosing the right model architecture is crucial for the success of a multimodal AI model. Various architectures can be utilized depending on the specific requirements of the task at hand. Convolutional neural networks, CNNs, are popular for processing vision data due to their ability to capture spatial hierarchies in images. For sequential data, such as text and audio, recurrent neural networks, RNNs, and their variants, like long short-term memory, LSTM, networks, are often used. These models are adept at capturing temporal dependencies. In recent years, transformers have gained popularity for multimodal AI tasks due to their ability to handle both sequential and non-sequential data. Transformers use attention mechanisms to weigh the importance of different data parts, making them suitable for integrating diverse modalities. When choosing an architecture, it's important to consider the nature of the data and the task requirements. Often, a combination of these architectures, such as using CNNs for image processing and transformers for text and audio, can provide optimal results for complex multimodal integration tasks.
Fusion strategies are key to integrating data from multiple modalities in a coherent manner. They determine how and when data from different sources are combined within a multimodal AI model. Early fusion involves combining raw data from all modalities at the input level before feeding it into a single model. This method requires that data be preprocessed to a compatible format, ensuring that the model can process the integrated input effectively. Late fusion, on the other hand, involves using separate models for each modality and then combining their outputs at a later stage, often using techniques like weighted averaging or voting mechanisms. Intermediate fusion is a hybrid approach, combining data at various stages of the model to leverage the advantages of both early and late fusion. Choosing the right fusion strategy depends on the specific characteristics of the data and the desired outcome. For instance, early fusion might be suitable for tasks where the modalities are closely related, while late fusion can be beneficial when each modality provides distinct insights.
Training and fine-tuning are critical phases in the development of multimodal AI models. The training process involves feeding the model with labeled data and adjusting its parameters to minimize error, thus improving its accuracy and performance. Fine-tuning is an extension of training, focusing on adjusting the model parameters to enhance its performance further, often done after the initial training phase. This is particularly important for multimodal models, as they have to balance learning from multiple data sources. One of the common challenges during training is overfitting, where the model performs well on training data but poorly on unseen data. Techniques such as dropout, regularization, and cross-validation can help in mitigating overfitting. Following best practices in training, such as setting appropriate learning rates, batch sizes, and using validation datasets, is crucial for achieving optimal model performance. There are various tools and frameworks available for training multimodal models, such as TensorFlow, PyTorch, and Keras, which provide robust support for handling complex data and model architectures.
Evaluating the performance of multimodal AI models is an essential step to ensure they function as intended. The evaluation process involves using metrics that reflect the model's accuracy, precision, recall, and overall effectiveness across different modalities. For text data, metrics like BLEU scores and F1 score are commonly used, while vision data might be evaluated using metrics like accuracy, precision, and IOU, intersection over union. Audio data evaluation often involves metrics like word error rate, WER, and signal-to-noise ratio, SNR. Assessing cross-modal performance is crucial, as it ensures the model is not only performing well within each modality but also effectively integrating and responding to the combined data. Challenges in multimodal evaluation include ensuring that the metrics used are appropriate for each modality and that the evaluation process accounts for the complexities of multimodal integration. Tools like TensorBoard and custom evaluation scripts can aid in this process, providing insights into model performance and areas for improvement.
Multimodal AI models have a wide range of applications in the real world, showcasing their potential to transform various industries. In healthcare, these models are used for diagnostics, combining data from medical images, patient records, and even audio data from consultations to provide comprehensive insights. In autonomous systems, such as self-driving cars, multimodal AI integrates data from cameras, radar, and LiDAR to navigate and interpret complex environments safely. Natural language processing benefits significantly from multimodal AI, as it enhances machine understanding of human language by incorporating visual and audio cues. This is particularly useful in applications like virtual assistants and customer service bots. Looking forward, the future of multimodal AI is promising, with trends pointing towards more sophisticated integration techniques and applications in areas like education, entertainment, and beyond. As these models continue to evolve, they will undoubtedly play a pivotal role in advancing AI capabilities and applications.
Let's explore some case studies that highlight the successful implementation of multimodal AI models. In healthcare, one notable example is a model developed for early diagnosis of neurological disorders. By integrating MRI scans with patient history and genetic data, this model was able to significantly improve diagnostic accuracy and treatment outcomes. In the realm of autonomous vehicles, a leading car manufacturer developed a multimodal AI system that integrates data from various sensors, including cameras and radar, to enhance vehicle safety and navigation. This system has been instrumental in reducing accidents and improving autonomous driving capabilities. The entertainment industry has also seen the benefits of multimodal AI, with models that integrate audio, video, and text data to create immersive virtual reality experiences. These case studies not only demonstrate the potential of multimodal AI but also provide valuable lessons on the challenges and best practices in real-world implementations. They underscore the importance of effective data integration, model training, and performance evaluation in achieving successful outcomes. As we conclude our hands-on guide to building multimodal AI models, let's recap what we've learned. We explored the components of multimodal AI, the importance of data preprocessing, and techniques for aligning different modalities. We also discussed various model architectures, fusion strategies, and the crucial phases of training and evaluation. The future of multimodal AI is bright, with opportunities for innovation and advancement in numerous fields. We encourage you to experiment and apply the techniques discussed, utilizing the resources and tools available to further your learning and development in this exciting field. Thank you for joining us on this journey, and we look forward to seeing the innovative multimodal AI solutions you will create.